all for coming. I am Yves Lejean, visiting professor of mathematics at NYU Abu Dhabi. And it is a pleasure for me and an honor to introduce Michel Broué and welcome him at this NYU Institute, NYUAD Institute. So I think it's fair to say that Michel is a worldwide famous mathematician. He holds a chair at Paris Diderot University and visited also many prestigious institutions such as Cambridge, Berkeley, the ETH of Zurich, and Beijing University, where I think we met for the last time. It was the last time we met in Beijing, Beida, last year. He is also a fellow of the American Mathematical Society. In mathematics, Michel's fields of interest are wide, but it is not the time for explaining in detail what they are. Anyway, I wouldn't be the best person here to discuss them, as is the chief editor of the Journal of Algebra, and myself rather focusing on probability theory. But let me say that besides its research, Michel has been very active in teaching scientific policy and organization, and also at interfaces between mathematics and other intellectuals or artistic fields like history or theater. As we have known each other for some time now, the Faculty of Mathematics here have been kind enough to let me introduce him. So Michel, teach us what are these mathematical myths and misconceptions.
Thank you. Well, I'm very happy to be here. Coming from Paris and this low and gray and depressing weather, it's such a pleasure to be under the sun. I want to talk about mathematical myths and misconception, maybe perhaps partly because I'm French. And in France, mathematics is viewed as a kind of oppressive field. It is the main field which is used to select people, select students, select executives, select, etc. And it's viewed as I say, an oppressive field. On the contrary, we mathematicians think that mathematics is the essence of freedom. And so I want to explain, to give you some of the misconceptions about mathematics, to answer, to destroy these misconceptions, and then switch to the positive aspect of mathematics. So let me start with a nice picture which I like very much, which is due to Escher. And this is two tetrahedron, which are one to the other, and I will explain why it tells you in a few minutes. I will explain that there are particular instances of the Platonic solids, and it's a kind of self-dual Platonic solid. You'll see why it has something to do with mathematics and misconception. So the first wrong idea that people have, at least in France, is about the golden age of mathematics. Some of them think that the golden age is the antiquity. You see, Euclid, geometry, logic, triangle, etc. And sometimes I've been asked the question, what are you doing? Everything is known about the triangle. What is it to be a mathematician? Well, by the way, not everything is known about triangles, but being a mathematician is not only working on Euclid. So it could, some others say, well, those people who found the zero, who found how to write numbers, which we are still using, actually. We are still using the Arabic numeration. Some other people think that this is the Descartes, so we are back to France for a while, Descartes' way of, turning the geometry into algebra, being able to do computation to understand geometry, which is indeed very important. Then some other people think that the infinitesimal quantities which have been used by Newton and Leibniz, allowing the work of all the analysts, all maybe 80% of the actual mathematics is the golden age. But they are all wrong. The golden age of mathematics is nowadays. Really, it's nowadays. It has been the 20th century and the 21st century. And I just want to quote that there are, as I said, 1,500 journals a year containing between 200,000 and 300,000 articles per year, and in almost 100 languages. So mathematics is active as it has never been in the last few years. And mathematics are absolutely everywhere. And of course, my list is not exhaustive. In your eyes glasses, the geometry of the eyeglasses, you see the one, I don't know if it's called, the one which change when you look like here and you there. They rely on some precise geometry, and they were not known 50 years ago. Of course, in internet. Of course, in the digital music, the encoding of the digital music uses some mathematics from the 19th century. Mathematics from the young French genius Évariste Galois, who could never imagine that these mathematics will be used one day by CDs and DVDs, but it is the case. Of course, it's used in medicine by the magnetic resonance imaging. It's used in traffic regulation, in internet, in regulation of internet. It's used in military and banking secrets. It's used when you use your Visa card or whatever, your MasterCard. I don't want to advertise any card. It's used in DNA. It's used in data mining. I don't know if everyone knows what is data mining, but it's something which is, no, I don't explain. I can answer a question about data mining. And of course, as usual, it's used in physics, biology, finance, etc. It's absolutely everywhere, even if you are not totally aware of that. Okay, the second wrong idea about mathematics is that mathematics require obedience. In France, we would say that the mathematical teacher would knock on your fingers if you give the wrong answer. On the contrary, we think that mathematics is the only area in the teaching system where the student can prove his teacher that the teacher is wrong. He can prove that. There is no other field where you can prove your teacher that he's wrong, right? And it's why a very well-known mathematician, Laurent Schwartz, who got the Fields Medal in 1950, used to say that good mathematics are subversive. Good mathematics are those who don't believe just what is told to you. You just think by yourself, right? Another example in history, the Indian, so-called Indian Mayas, used to know the value of pi, you see this strange number which has something to do with the circle, okay? Up to 8 decimals. They knew that. But at that time, they had to do with the Spanish church and the bishop of Yucatan in order to burn all these devilish lies. I don't know why he didn't like pi to be that complicated, but he didn't like it. It's like this. But mathematics were not teaching to obey. They were teaching, you see, the contrary. But I want to concentrate, and this will be the opportunity to give you the only proof, because I do want to give a proof. This is a mathematical talk, after all. So I want to tell you the story of square root of 2 and of this Hippasus of Metapontum. It was a long time ago, you see, 5th century before Christ. It's a long time ago. So since some of you are not mathematicians, maybe I should start with saying a few words about square root of 2. What is square root of 2? The square root of 2 is the non-negative number whose square is 2. For example, square root of 9 is 3, because 3 is the number whose square is 9. All right? Okay. So I'm looking for square root of 2. First of all, we can note that there is no natural number whose square is 2. 1 to the square is 1, 2 to the square is 4, it's already too big. 3 to the square is 9, etc. So it's too big. So there is no natural number. So is there a fraction whose square is equal to 2? And even the Greeks, the ancient Greeks, raised the question whether this number exists. Is there a way of seeing this number? And they knew it, and let me tell you how they knew it. It's interesting. Socrates knew it. So here's Socrates' solution. This is mathematics, right? So for 2 minutes you concentrate, right? Okay, let's build a square with size 2 by 2. Okay, so half the line has length 1 whatever you like. Okay, 1 meter if you like, 1 centimeter. Okay. Now we draw the interior diagonal square like this. All right. Then we call d the length of one of these sides. All right. We shall see that d is actually, this length is square root of 2. I am going to prove that. Socrates did it a long time ago, so you can understand that. Okay. So let's draw the diagonal of the small square, this line inside. So we are back to this situation. The big square, size 2 by 2, then the internal square, and then the diagonal of the internal square, okay? And the length of the small square is d. Now, let's prove that d is square root of 2. To prove that d is square root of 2, we have to prove that d to the square, to 2, d to the 2, is 2. All right. So what is the area of the small square? You see the small square, you just double it here, you double it here, you double it here, and there. So it's obvious that the area of the small square is half the area of the large square. You agree? So now let me compute the area of the small square. This is d to the power 2, because the area of a square is the length of its side to the square, right? So d to the square is half the area of the big square, which is 4. So d to the 2 is 2, right? Which proves that d is square root of 2. So the Greeks knew that. They knew how to build square root of 2 as the length of something in the field, whatever. And now the natural question which came into their mind is, what is the ratio? Because they didn't think in terms of fractions, of rational fractions. They thought in terms of a ratio, but it's not essentially different, right? So what is the ratio which is equal to that number square root of 2? And then came a fantastic surprise. And the fantastic surprise is that there is no ratio which equals square root of 2. And that was a big outrage against the way of thinking of these ancient Greeks. They couldn't believe that, they couldn't accept that. But let me show you why it's true, and this is the real mathematical demonstration I want to do for you now. And this is this poor Hippasus of Metapontum, who is supposed to have found this outrageous fact. Assume that square root of 2 is a fraction, is p over q, where p and q are natural numbers. Now let's do real mathematics for 2 minutes. Since p divided by q is this number, we can always assume that at least one of them is not even, because if p and q were both even, we can divide by 2 both sides of the fraction if the result is the same. So let's assume that one of them, either p or q, is not even, right? And this is allowed, but we'll find a contradiction. The contradiction will come from the fact that we assume that square root of 2 is p over q. So that will prove, if we reach a contradiction, that it's not possible, that square root of 2 is not a ratio. So since p over q is square root of 2, that means that the square is 2, so which I wrote. So that implies that p to the 2 is 2 times q squared. You know that. Okay. But now look, if a square is divisible by 2, the number itself has to be divisible by 2. because if the number is odd, the square is also odd. You agree with that? So P has to be even. So P has to be 2 times some other number, P prime. Okay, so let me replace P by 2 P prime. So P square is 4 P prime square. Okay, so if I replace P square here by 4 P prime square, I get this equality. Then I can divide by 2 both sides, and I get 2 P prime square is Q square. All right, that's enough. End of the argument. Because now Q square is even. For the same reason, Q has to be even, because if Q were odd, then Q square would be odd, right? So Q is even. But what did I say from the beginning? I suppose that one of them at most is even. And I found that 2 are even. P is even and Q is even. This is a contradiction. A contradiction with the only hypothesis I made, which is that P over Q is square root of 2. And this is, not only this is a contradiction, but for the Greeks that was outrageous. That number is irrational. That doesn't mean that it is against the reason. That means that it is not a ratio. Okay, it comes from that. Well, according to some legend, that cursed fact was discovered by Hippasus of Metapontum, okay? And he's supposed to have drowned in a terrible tempest because at sea. Apparently because as it was a punishment for the gods for the facts he had found, and he had let people know. That was a terrible. Of course, that make us laugh today, but it was a terrible revolution. Like when we finally accepted that the Earth was not a circle centered in Jerusalem. It's not a circle center in Jerusalem, right? It's a sphere. But when we discovered that was terrible also. So this is part of the role of mathematics. And this is why they don't teach to obey. They teach, in a sense, to... You see, this story of Hippasus of Metapontum is a kind of great story in the glory of disobedience, I would say. Because he's right. Quite another aspect of wrong ideas about mathematics. Mathematics are cold. They provide no pleasure and certainly no passion. Can you imagine a mathematician who is passionate with mathematics? You're wrong if you cannot imagine that. Let me quote 3 people for different aspects. The first I want to quote is André Weil. André Weil is probably one of the greatest mathematicians of the 20th century, founder of Bourbaki. For those who know, he's also the old brother of the philosopher Simone Weil. He wrote extraordinary texts about mathematics. He was also a big connoisseur of India, of Indian culture, of ancient Greece. And he wrote extraordinary texts about mathematics and the creation in mathematics. And I just want to extract from one of these texts. Let me just speak French, just for my own pleasure, for 2 minutes. Rien n'est plus fécond, tous les mathématiciens le savent, que ces obscures analogies, ces troubles reflets d'une théorie à l'autre, ces furtives caresses, ces brouilleries inexplicables. Rien aussi ne donne plus de plaisir aux chercheurs. So for those who didn't understand, let me just translate some of the words that André Weil used. He said, troubling reflex, stately caress, inexplicable tiffs. So this is mathematics. Something different, Kepler. So not the same century, not the same nationality. Kepler was the one who found these extraordinary laws of how do the planets go around the sun. Still today, I can't understand how it did, because the Kepler's laws are extraordinarily precise, and they're true, essentially true. So I'm going to check just the first one of these laws. The other ones are too difficult, too technical to be quoted here. The first law requires the notion of ellipse. an ellipse, so on the left you have the French drawing, and on the side you have the English drawing. So they are the same, but the French drawing is just more precise. So you take two tacks, pin them, okay? You take a string, and you take a pen, and you fix the string with the tack, and you let the pen run by like this, like it's written, okay? You see that if you extend the tacks so up to the length of the string, you get a part of the line. And if on the contrary, if you put the two tacks together, then you will get a circle. So you go from a circle, which becomes flatter and flatter and flatter, up to get a line. This is the ellipse, like this. All right. And the first of Kepler's, this is the ellipse, and the place where the tacks are pinned are called the foci, one focus, two foci, of the ellipse. And the first of Kepler's laws is that the orbits of the planets are ellipses with the sun at one focus. You may ask the question, why at one and not the other one? It's like this. This is Kepler's law, all right? This is already very astonishing, right? Try to sit in front of the sky and try to deduce by looking at the sky that the orbits of the planets around the sun are ellipses with the sun on the focus. Try to do it just to see. All right, second law. The second law is more astonishing, you see? It says, let me state it, that the line joining a planet to the sun sweeps out equal areas in equal times as the planet travels around the ellipse. That means that, you see, when so let me, as equal time, I choose 1 month. So if the planet is far away from the sun, the area will be large with a small distance traveled by the planet. So in 1 month, it travels like this. But if it is close to the sun, closer to the sun, it has to travel more to get the same area. So that means that the planet goes faster as he approaches the focus where the sun is, and slower when it is far away. That also was noticed by Kepler, alone with his little hands and little and big brain. And big brain. Okay, and what did Kepler say when he published that? Listen to his pride. And this is also a kind of passion. So it has to be quoted in full extent. Now, because 18 months ago, the first dawn, 3 months ago, broad daylight, but a very few years ago, the full sun of the most highly remarkable spectacle has risen, it means that he has understood everything, what it means. Nothing holds me back. I can give myself up to the sacred frenzy. I'm indeed casting the die and writing the book, either for my contemporaries or for posterity to read. It matters not which. Let the book await its reader for 100 years. God himself has waited 6,000 years for his work to be seen. He was proud, right? But he was right. It was such an achievement, right? So you may ask why he says 6,000 years. This is another question. All right, and finally, the guy I want to quote is Jean-Pierre Serre. He's still alive, fortunately, and still very active, although he's what, 86 years old. Very active, skiing and climbing up rocks and doing and doing great mathematics. And once in the journal Libération, the French newspaper Libération, he advertised in mathematics to practice when you are proving things. I won't explain. I just quote that. The demonstratio interruptus. The pleasure that you take by just stopping in the middle of the proof and going for a walk because you are too excited. And then you come back and you finish. You have to. So this is for the mathematics. We have no passion and no, which are cold, etc. The next idea I want to fight is the idea that mathematicians spend life embedded into their own computations. That is completely wrong. On the contrary, the essence of mathematics consists in taking some distance, in viewing things from far enough to discover strong similarities between apparently totally different problems. And for that, let me give you some examples. For example, the following assertions, which are quite different, from the mathematician's point of view, they are absolutely equivalent. So some are easy to understand because they are from everyday life. Some are not so easy to understand. They are mathematical assertions, so they are just for those who know complex numbers, for example. But never mind. The first assertion, so they are all the same thing for a mathematician. It's impossible to comb a hairy ball. What a strange idea, but never mind. To comb a hairy ball so that it becomes all smooth. If you can find a hairy ball, try to comb it. All right. Second assertion, if P is a polynomial with complex coefficient and degree at least 1, then the equation P of Z is 0 has at least one solution in the field of complex numbers. This is equivalent. Third assertion, there is at least one spot on Earth, our old Earth, where the horizontal component of the wind is 0. You see the wind blows, but maybe it doesn't blow horizontally, maybe not also vertically, but except in some catastrophic event, but sometimes it blows like this. So you have, it's a kind of vector, you have an horizontal component and vertical component, and I think that what I mean is that the wind is vertical at least, or 0. But there is always at least one spot on Earth where the horizontal component of the wind is 0. This is equivalent to the preceding time. And of course, to come back to the first thing, because it's the same thing, it's impossible to, or it's always possible to find a tuft in the hair of a bear, or a mouse, or a cat, or a dog, or whatever you like. It's always possible. Okay, as you understand, certainly it has something to do with the airy ball. Let me give you other examples of quite different problems, which for the mathematicians are exactly the same. The marriage laws in the Aboriginal tribe named Walpiris. This was studied in particular by the big scientist, ethnologist, you say, Claude Lévi-Strauss in France. The law governing the geometric transformation which sends a square onto itself. You see, you can turn a square like this, it remains the same. Turn a little like this, it remains the same. You can also switch it along the diagonal, it remains the same. These laws. And the laws expressing the relation between the complex roots of the polynomial e to the 4 minus 2. So the marriage law, the square moving, and this polynomial, they are the same thing. They are expressed by the multiplication table of a group, which is a dihedral group of other 8. In the first attempt to prepare this talk, I draw this table, but it's too long to explain. But you have to accept that these three things are the same. And just to please my colleague from probabilities, let me quote the random walk. Suppose that you take what is a flat die? It's a coin. Flat die is a coin. So you play and you say that it's come on one side. You are on a line. You have a mobile on the line, and if you find if the result is one side of the coin, you go left. If the result is the other side, you go right, and you play. You can play this game on a piece of paper, and then you need a tetrahedral die that exists, and you play with the tetrahedral die. Either you go up or left or right or down. Okay, you can also play that in the space with ordinary die, the 6 faces, right? And you play whether you go, etc., etc. And now you raise the question: what is the probability to get any point? First of all, on the line, you start with 0, say, and you go left or right according to chance. My first feeling when I was asked first this question is that, well, if you go far enough, you will never reach the point because it's too far away. And the same thing in the plane, right? Actually, the answer is kind of surprising, the first, if you don't perform the computation. The probability of never reaching a point is 0 for the line. That means that you will always reach a point, essentially, if you go that long enough. It's 0 in the plane. But it is 0.65 in the space, which means that most of the time you will miss many, many, many points. So it's a strange answer, but it's like this. But I want to say that this type of things has something to do with the Brownian motion. And the Brownian motion has something to do with the physics, of course. It's why I quote Brown, I quote Einstein. And also with computer science is why I call Norbert Wiener. It has also lots of things to do with market fluctuations. So in a sense, this story of flat die or tetrahedral die, etc., has something to do with market fluctuation. This is also the distance which is taken by the mathematicians. Okay. And the last critics against mathematics is that they invent the object they want to study. They invent the study. They are, of course, it's easy because they are studying just what they want. This is wrong. They study what they find, which is different. And let's tell a few facts about Platonic solids. If you raise the question of, before talking about Platonic solids, if you raise the question of drawing a figure which is a kind of first approximation of the circle with sides which are all equal, a polygon, you want to, a polygon with 3 sides is triangle, right? With 4 sides is a square. With 5 sides a pentagon, and you can go on. Hexagon, heptagon, octagon, and you can go on forever. N-gon, clear. And if you go on forever, you reach the circle, approximation of the circle, very well. Now it's quite natural to say what is possible to do in the space. So instead of drawing or considering approximation of the circle, you can look for approximation of the sphere. So you want solid whose faces are all the same. What a surprise, and what a surprise for the ancient Greeks, once again, that the answer has nothing to do with it. Here you have an infinity, as many polygons that you have integers. In space, this is totally different. Of course, you know an answer. You know the tetrahedron already quoted. Here you have 2 tetrahedron. But what else? The answer is you have only 5 such solids. Only 5. They are called the Platonic solids. While in the plane, you have an infinity of such things, okay? If you want to approximate the sphere, you have only one, which are these guys. Plato almost used to know it, and they are nowadays called the Platonic solids. They should be pinned in every history or philosophy class, or I mean, they are a kind of datum of mathematics, hard datum of mathematics, but also of universe, of the world, okay? So I won't give you details about the Platonic solids, but if you know a little bit of Greek, you would know what ikosa comes from, that dodeca comes from dodeca, has something to do with 12, the other one with 20, but okay, anyway. So these are and the only one. And not only that, but it's not exactly 5, it's rather 3 for the reason I'm going to explain. So on the left, I put the 5 Platonic solids. But what did I do here? I take the cube, and in the middle of each side of the cube, I put a point, and I join them. You see, I put a point in the middle of each side of the cube. And why do I get? I get the octahedron. So I get one of them. And if from the octahedron I do the same, I put a point in the middle of each side, I get the cube. So the octahedral and the octahedron and the cube are kind of dual, as we say, from each other. You see, you replace the faces by the point, and you get the other one. So they go together. Is it exactly the same thing for the icosahedron and dodecahedron? You get one from the other, and vice versa. And so we have used 4 of them. So one is left, the tetrahedron. But we know that if you do the same treatment of the tetrahedron, you get the tetrahedron. It's self-dual. It's what I announced from the beginning. Okay, this is well known. This was known in the Neolithic age. Was discovered in Ireland, for example. So, was it invented by mathematicians? Of course not. This is one of the laws of the universe. That's it. It's not discovered by mathematicians. Now, let me just go quickly to tell you that it was so astonishing for the Greeks that they decided that these 5 solids had to have a meaning, you see. The tetrahedron was the fire, the cube was the earth, the octahedron was the air, the icosahedron was the water. And unlucky enough, they missed the dodecahedron, which was discovered later. But they had taken all the things, you see. The air, the earth, the fire, everything was taken. So what should they do? So, as I said, it's kind of an embarrassing discovery because it's not 4, it's 5. So Plato proposed to associate the dodecahedron to a 5th physical element, the ether, and it was the physical element which is not considered as existing nowadays, but it was hard to die. And anyway, so you had this association of the. Notice that the cube is called here hexahedron because hexa stands for 6, and it has 6 faces. All right. Let me continue with this wrong fact that mathematicians are inventing the object they study. Let me do a little bit of arithmetic now. Let me speak about prime numbers. You all know what a prime number is, right? A prime number, let me say that the prime number means that P balls or matches or soldiers or whatever cannot possibly constitute a rectangle, right? It's what it means. If, of course, except a trivial rectangle, a single line or single column. And the major may yell if he has, say, 13 soldiers, they cannot stand in the rectangle because 13 is a prime number. All right? It's a number which is divisible by no other number but himself and 1. This is the definition. So look, this is the sequence of the first prime. I give you this because each time you explain what a prime number is, you say 2 is prime, yes, 3 is prime, yes, 5 is prime, yes, and the guy say, oh, I understand, 7, 9, no, 9 is not prime. Okay. So this is the sequence of first, but also there are some others, right? Much larger, and even one which is much larger. That means 2 times 2 times 2 times 2, 21,701 times. It's big. It's very big. And this number is prime also, all right? Okay, these are prime numbers. I don't have so much time, but let me notice something which is very surprising. If you take 17 and 19, or 29 and 31, or 109 and 103, but also this number here, which I don't read, and that number here, okay, they differ just by 2. You see, they differ by 2, and you may go as far as you want. You will always find a pair like this. It goes to the infinity, so to speak, of prime number which differ by 2, but it's not known. I mean, it's known by computers. It's you have always find as far we could go with computers, but there's no definite proof of that fact. This is one of the conjectures, as we say, which is still open about prime number. We don't know whether it's true. Of course, each time you check that, it works, but you don't go to the infinity. You are not God yourself, just a man. All right, but this is not my point. So let me give you an arithmetical theorem, which is difficult enough to be taught in end of undergraduate or maybe beginning of graduate studies, which you can understand perfectly in concrete terms. And this is also not the will of mathematicians, this is the reality of nature. And it goes that way. let's take P a prime number, for example, 13. So take P ball and arrange them by pack of 4, as many as possible. So for example, for P is 13, you put 1, 2, 3 pack of 4, you get 12, and 1 is left. Okay. Notice that when you do this, you're left with only 1 or 3. You're left with something, because if you are not left with something, the number is in a big rectangle. It's not prime. And if you're left with 2 balls, well, you can regroup, and you get a rectangle. The number is not prime. So, indeed, you are left with 1 or 3. It's a rule. Okay. We are left with 3 for P is 11, and you are left with 1 if P is 13, etc., and it goes all the way. And actually, I give you an exercise. This number, which I cannot read except by saying 1, 2, 3, 4, 5, 6, 7, 8, 9, 1. So this number is prime. It's a fact. And if you do that, you're left with 3. So why? This is the exercise. Why are you left with 1 when you do that? All right? Now the theorem is, if you're left with 1 ball, you can always rearrange the set of balls into 2 squares. I'll show you the example. And if you are left with 3 balls, it's impossible. So let me show you what I mean. If you're left with 1 ball, for example, P13, you can arrange that to 2 squares. Indeed, 13 is 9 plus 4. So it's 3 square plus 2 square. And this is always true. This is a theorem which is true for, and you don't have to check it. It is true. It is the strength of mathematician to say in advance it is true. So for example, what about this number? This is not an exercise. This is not easy. Because the mathematician will tell you it's possible to arrange them into 2 squares, but it won't give you the size of the squares. So this is not an exercise. I just raised the question, what about these 2 numbers? All right. Now let me switch for 5 minutes to the positive aspects of mathematics, having fought some of the myths and misconceptions about mathematics. First of all, let me say that one of the advantages of mathematics is that common sense may have a hard time with mathematics. We could do an experiment here, a lot of experiment actually. I can start with what I call the paradox. It's not the paradox, but it's easy to prove once you think. But of the rope around the Earth, it goes that way. Let's circle the Earth along the equator with a rope, and then I change my mind. I want to circle the Earth along the equator with a rope, but at 1 meter high. You see, with a certain distance. How much longer should be the rope? The answer is 6.20 meters, roughly. But the point is that the answer would be the same. It doesn't depend on the Earth or the size of the Earth. The answer would be the same if you replace the Earth by any sphere, by an orange, or by the moon, or by a ball. You always have to extend the rope by 6.28 meters. Of course, mathematicians know that it comes from the fact that the circumference is the linear function of the radius of the sphere. But for the guy who sees that the first time, he's kind of astonished. But it's true. Perform the computation, you will see. Now, there is another experiment that we could do here if we had time. The paradox of the anniversary. Suppose that I ask you at the end of the talk to write your birth date on a sheet of paper. I'm certain, I bet my own head, yes, that at least 2 of them have the same birthday. Actually, the probability, let P of n denote the probability, so that given n persons, so here is what, 100? Niels? 150 or 60. So the probability for that given n persons chosen by chance, at least 2 of them have the same anniversary date. This probability when it is larger than 1/2. So when is it that you have one chance out of 2 to find the same date? It suffices that n is 23. If you take a classroom of 35 students, for example, you are almost certain that 2 of them will have the same anniversary date. Surprising, isn't it? Actually, for p is 50, it's already 97% of chance of finding the positive residue. For 150, it's already 100. So I'm sure, if you don't believe, you can take my head, if you can. And the same paradox, but it's more striking. It's not a paradox; it's computation. But it's more striking if you do this way. A human being has an average of 100,000 to 150,000 hairs on his head. You have to believe me, because no one ever counted the number of hairs, right? But roughly, okay. Now take a small village with 2,000 inhabitants. What is the probability for 2 inhabitants of this village to have exactly the same number of hairs? 125, say, for example. 100,025 hairs, exactly the same number. 2,000 people is not much, right? Compared to 100,000 hairs. Well, the probability is 99.99%. It's like this. True. Okay. Maybe I won't quote the normal decimal numbers. I can answer a question about that. But I want to perform the Mobius Strip thing because I prepare it, so I want to do it. You know what is the Mobius Strip? You take a ribbon and you twist it one time and you glue it. Okay, it's known because of Escher, for example. You see the ants walking on the Mobius strip, and they start on this side and they keep on walking, and they arrive on the other side. It's a surface which has no interior nor exterior. But it's not what I want to do. I want to cut it in 2. Okay, so I cut it in 2 along the long side. So I cut it in 2. There is no suspense. I know the result, but. It's long. Okay, I cut it in 2, so I should get how many pieces? 1. I'm not a prestidigitateur, magician. I'm not a magician. I'm just a mathematician, right? And if you cut it in 2, you may raise the question. If you cut it in 2 once more, what do you get? You get the same thing now. You get the same thing as this one, which is twisted twice, but with a big knot linking them. Yeah, and you can go on if your strip is large enough, right? So this is what mathematics has to do with common sense, right? They bring order into chaos. Let me quote that. For example, order within pi, the number pi, the circle. The disorder is this sequence of digits when you want to know pi, what pi is. The sequence is so strange that you have some sites where you give your birthday, complete with the year. You can add up, if you want, any number you want, in front, behind. You enter this number, and the site will find it for you in the same order, the sequence of digits in the decimal writing of pi. It contains everything. It should. It has great chances of containing any type of sequence of digit. Okay, so this is the disorder. And where is the order? Okay, you compute 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9. You understand how I go on, right? You compute that on a computer, and you see that it slowly goes to a number which you multiply by 4, and it's equal what? Pi. So this this is the order into chaos. By the way, there is another thing which is funny. Even if I'm a bit late, I want to quote it. This is the so-called Buffon's needle. Suppose that you have a pocket with 10 centimeters large laths, and you take a needle which is 10 centimeters long, and you drop the needle. And you count the number of times the needle lies across a line, or a number of times it doesn't. So I explained on the drawing, you see, this needle lies across a line and this one doesn't. All right? You count this number and you perform that many, many times. Then the probability that the needle lies across a line is 2 over pi. This is a way of computing pi. There is a crazy guy who did that, actually, in the 19th century, a guy named Wolf. He dropped a needle 5,000 times. But it's not a very efficient way of computing pi, but he got 3.5 as the first approximation. But if you do it 50,000 times, then you'll find good approximation for pi. So this is kind of, is it order or disorder? I don't know. But this is, okay. And finally, they make it possible to represent the world. You see, for example, and I will end with it, an infinite yet bounded universe. Here is Henri Poincaré's hypothetical universe. The universe is contained in the interior of a sphere, which has the following properties. The temperature of the universe is very high in the center and gets cooler and cooler and cooler and cooler and very cool as you move towards the surface of the sphere, the exterior of the sphere, right? To be more precise, to give at least one formula, if capital R is the radius of the sphere, and if little r is the distance from the center, then the temperature is capital R square minus little r square. So the temperature is really 0 on the border, all right? And the size of the objects inside the universe is affected by the variation in temperature. So the length of any object varies in proportion of the temperature. On the surface, where little r is, capital R is, so T is 0, the length of an object will be 0. So look at the picture. The objects are big in the center, and they tend to diminish in size when you move towards the side. And to diminish, and they vanish. Okay? And so an object traveling towards the edge of the universe will diminish in size because it gets cooler and smaller. So it can never actually arrive at the true edge of the infinite universe because, and also inhabitants are unaware of the changing temperatures. They have no sensitivity of this. Exactly, it's a strange world. Okay, but maybe we are like this, who knows? And so they measure the object with the object they have, but the object they have are just diminishing as soon as they get on the, so for them it never ends, right? Okay, so they never get to the boundary because the nearer they get to the boundary, the more rapidly they shrink and the smaller the steps become, right? So although the universe is finite and bounded because it's a sphere, to the inhabitants, the universe is infinite. So it's like this. You do look, I put the picture and I put a poor guy living in this universe. He always thinks he's normal, but it's harder and harder to get to the border, right? This is a way of thinking of a bounded universe. And only mathematics can give you this a kind of possible solution to this paradox, the universe bounded, right? I think I stop. I wanted to quote Einstein, and I wanted to quote Turner, because Einstein makes me think of Turner and vice versa. I wanted to quote Plato with moral and beauty, and I wanted to end with, of course, the golden spiral and the beauty of mathematics. Thank you.
Why do we believe these things about mathematics?
As I said, in the beginning, one of my explanations is typically French. It's because mathematics is used to select people, and people used to dislike mathematics. Because when they failed, they disliked, they say, well, it's jerk. No, I don't know. I don't know. It should teach freedom. It does teach freedom. But maybe it's the way it's taught. Maybe it's the way it's taught. Very often it's taught like teaching obedience, while it should teach disobedience, as I said. I'm aware that my answer is not satisfying, but it's a fact.
The fact obedience, for example, sometimes, I mean, you can actually prove that someone is wrong. It can be the teacher who proves that to the student, or
sure.
the converse. More often it's the teacher, let's say. So in a sense, you can prove that you are wrong or prove that you are right. Mm-hmm. And absolutely. And this is not true in every.
Yeah, but this is not obedience. This is intelligence.
No, that's
this
true.
is rationality. This is.
Right.
There's nothing to do with obedience.
There is something unavoidable in it.
Yeah, sure. There's something unavoidable, certainly. But this unavoidable is just above us. It's above all the laws that people have invented to. That's it. Yeah, I agree. It is rigid because it's wrong or true. This is true. Mathematics is kind of, well, it's an easy world also. It's quite a rest from the rest of the world. You can take a rest in mathematics. I feel at ease because it's wrong or true. In the everyday life, it's not as simple as this, right?
A question, we had here a presentation some time back on music and brain. What's your view on music compared to mathematics? They say good mathematicians are good musicians, and the contrary. Can some of your theorem or axiom be applied into music? Well,
first of all, before coming here, I hesitated to give here a talk about harmony and mathematics, yes, because especially we group theorists, specialists of theory of groups, have a way of looking at harmony, which is kind of enlightening this area. So certainly, the rules of harmony there are directly under the influence the rules of mathematics, no doubt. And for those who know, it's essentially the group Z mod 12, which controls the usual harmony, and we can do lots of things. So certainly there are, and some of these laws of harmony, which are presented as a kind of natural or divine or whatever, they are just ordinary combinatorics in group theory, that's for sure. Then the next assertion that mathematicians are good musicians and vice versa, I think is totally wrong. I know lots of mathematicians who have no sense of rhythm, for example. So they are not good musicians, no. No, but it's true that there is something, there is something in common. For example, how do we say fugue? How do one say, does one say fugue in English? Fugue? Fugue. Whenever a mathematician hears the fugue is delighted, because the construction has something to do with mathematical construction. It's so much clever and so much stable and so much. It's true that there are lots of construction in mathematics, and it was not a surprise that modern musicians have used mathematics to build up some music, which I don't like so much, but at least they tried, and it's quite natural. And also, I would say that I would end by saying that what they have in common is the search for beauty. And certainly in mathematics, we speak of harmony and beauty about a proof of our way of seeing at things. I remember I was 20 years old, I attended my first Bourbaki seminar, and all in the middle of a proof performed by the speaker, one of the guys in the room, actually it was Jean-Pierre Serre, so it was a very important in the audience, stood up suddenly and said, "Oh, this is disgusting what you are doing." Disgusting. He didn't say it wrong. He said it's disgusting. So certainly, yes, the notion of beauty and harmony and elegance and is as important in mathematics and in music. So this is certainly in common, and probably it goes beyond that, but I'm unable to develop now.
I am very envious, very frustrated. My great ambition when I was before I entered college was to be an astrophysicist, but I simply could not handle the higher mathematics. And I always felt that my undoing was not having the discipline and the diligence. So, okay, you say that it does not require obedience, but how about discipline and diligence?
Well, diligence, I'm not sure it is necessary. My own thesis advisor was a great mathematician, the founder of Bourbaki. His name was Claude Chevalet, and he would never understand when you would explain mathematics to him. When I was doing my thesis, I started to explain. After 10 minutes, he would say, would you write this for me, please? I knew that it meant that he didn't understand. He stopped understanding. He needed time. He was not quick. He needed time to understand. He needed to rewrite everything. And he rewrote everything from the very beginning. It was the only way for him to understand. So this diligence, as you say, is probably one of the ways mathematics are taught in secondary school or even in college. When you are, if you are not so quick, but if you manage to become a mathematician, you will see that, well, indeed, you have guys who are quick, but some others are not so quick, and they may be as good and as productive. The discipline, yes, is more, yes, the discipline certainly is important. Because the discipline, you see, it's also perhaps simply the intellectual honesty. The discipline is to be intellectually honest. You apply what you say to apply. You don't cheat. It's the paradox of the paradox to imagine a mathematician cheating. It's ridiculous. To do all this to cheat, is ridiculous. You see, so, well, so and so.
I have two questions. What are the great problems of mathematics in this coming century, and what is the role of technology in advancing mathematics?
The role of what?
Technology.
The
computer science.
the role of well, first of all, there is the computer science and computers are directly now applied to mathematics. Being a kind of abstract algebraist, it may sound strange to say that, but computers have changed my way of practicing my research. Lots of things can be experimented with computers, and now we do conjectures leaning on computers and computer calculations. So certainly from that point of view, technology has changed mathematics. This is a real revolution that we don't realize so much now. This is a real revolution in the way we are doing mathematics. Not only because some of the theorems are proved by computers, but because also we finally, after 2,000 years of practicing mathematics, we finally found the right tool, the computers. Then, of course, all of the sciences are influential because they are asking for help for mathematics. And nowadays, where I just mentioned internet or DNA and all that kind of problems, or data mining, which deal with enormous amount of money, billions of data, they are using probabilities and algebra and category theory and lots of things in a very amazing way. So they are certainly creating activity in mathematics. You can go to the site of the Clay Institute and you will see a list of the Clay, C-L-A-Y, Clay Institute, and you will find a list of the big problems for the century and the number of millions which are offered for those who solve them. But it will be too long to explain that.
I'm very interested in the question of whether or not mathematics is discovered or invented. And I think it's clear where you stand on that. I've discovered some work. I'm not a mathematician. In fact, I'm about as far from it as I am from the boundaries of the universe. So you have to bear with this question. But the idea that random patterns repeated over and over again can eventually give a semblance of order. So maybe a bit of there's an allusion to order, perhaps. And I was wondering if you could tell us why you're so convinced that mathematics are discovered and not invented.
I'm not convinced, actually. I understand that you think I'm convinced from the way I talked. But I'm not convinced. I would say I act as if they were discovered. And most mathematicians act as if. That's it. Now, has it really a meaning to say that the Platonic solids, for example, would exist without human brain, which is essentially the theory of the other side? The non-Platonicist guys say, well, mathematics is just a creation of human brain. They are not discovering, it's an emanation of human brain, that's what it is. So are the Platonic solid, yes in a sense and no in another sense, but yes in a sense because it's an abstraction and it's an abstraction of the human brain. It's a bit less clear for the prime numbers. I have the feeling, it's not a conviction, I have a feeling that if one day you have to communicate with people from other worlds, other planets, maybe it would be easier to see whether they have the notion of prime numbers. What? You see, is 13 divisible or not? Can you multiply 2? Can you put 13 in a rectangle? It's a very simple idea. And is it only the human brain? You could say, you see, if you think of physics, for example, in physics now they are dealing with these particles. They are quite real, right? The particles they can create atomic bombs. And destroy things, right? It's very real. Well, a particle is what? It's a wave, it's a particle, it's a probability. What is it? It's much complicated to understand than the notion of prime numbers. It's much more abstract, after all. And although it's quite concrete. So is it the invention of the human brain? Not sure the question is actually relevant. I wouldn't say I'm convinced, but I'm not convinced of the contrary either. So,
yeah, most great mathematicians seem to have been very productive at this specific age. Like these great mathematicians, Euler, Newton, Einstein. Newton had published his greatest book, his greatest scientific book, came up with his laws of motion, discovered calculus, discovered universal gravitation. Well, Einstein had published his special relativity paper, photoelectric effect, at this age of 26, 24, 26, 28. And then they do great jobs later, but then at this specific age seems to be very responsive to mathematics, I guess. It's from my own historical studies. What do you think about this specific age group? Do you see this trend, or is it just...
Oh, no doubt. No doubt that you need to be awake to do mathematics. You need to be active. You need to be inventive. You need to be subversive, as Lors was said. And a young guy is more easily inventive and subversive and imaginative than an old guy. And this is the list that you quoted can be extended up to lots of other mathematicians. So this is true that most mathematicians do the essential part of their work before 40 or 50, say. It's not by chance that the Fields Medal, which is sometimes compared to the Nobel Prize in mathematics, which is wrong. It's not the Nobel Prize. The Fields Medal is not given for the complete work. It's given for a precise and published result, one single. But it has to be given to someone who is under 40. It has to be given to someone who has done a great work, a great proof, a great theorem before 40. So it's not by chance. Still, there are many counterexamples of people staying very, very active until the age of, well, I quoted Serre, for example. Jean-Pierre Serre is 86, and if he goes to Singapore, if he goes to Chicago, if he goes to Mexico, if he goes to Amsterdam, he would fill totally the rooms where he's teaching or talking, because people know that he's one of the greatest mathematicians of his time at the age of 86. And he has always, still nowadays, he has something new to say, a new point of view on things, and a way of building bridges between different parts of mathematics, which is unique. So is a kind of counterexample to this rule, but I cannot say the contrary. The rule is in general is true.
If there's a circle that's as big as it can be and it keeps going towards the middle, can it get bigger?
Can you repeat?
His question goes back to the when you said the finite universe.
Yes.
If you went the other way, he wants to know if things will get infinitely larger if it's a infinite universe, I think is what he's trying to ask. If you go the other way and say that the universe is infinite and you move towards the center, do things get infinitely larger and larger?
Well, you can imagine that, of course, but that was not my point. My point was, of course, you can imagine that, except that the center infinite, I don't know, it would be difficult, but we can manage. but my point was to prove or to show by an example. It's not my point. This is Henri Poincaré's. Sorry, Henri Poincaré's point was to show an example proving that mathematics can handle infinity in a sense, in a finite picture, in a finite work, and this is much more interesting from my point of view, which I wanted to explain here. Now, of course, you can. Yeah, you know what youth is. Youth has a tendency towards imagination. So it's what he's proving now. He wants to do more. Right, great. He may be a mathematician one day.